Hello everyone, today we're going to be going over the 2026 FE Equals MA exam, problem 9. This problem is about orbits and energy. Let's start by reading the problem. A vertical cylindrical pipe with a sealed bottom contains no air and is tall enough that its top is open to outer space, which means it has no atmosphere. A heavy plate is mounted at the bottom of the cylinder and vibrates vertically. A small ball inside the pipes undergoes elastic collisions with the plate. The plate vibrates in such a way that during each collision, it is moving upward with a constant speed equal to v over 1000, where v is the orbital speed at 0 altitude above the Earth. The plate moves downward sufficiently fast that the ball collides with the plate only while the plate is moving upward. The ball is initially dropped from rest from a height equal to the Earth's radius above the plate. After how many collisions with the plate will the ball escape the Earth's gravitational field? Okay. So first let's draw a diagram of this. We have the Earth and we have this pipe. We have a ball oscillating, and then there's this thing that's moving up at v over 1000. Now, it says that the ball is initially dropped from rest from a height equal to Earth's radius above the plate. So initially, if I zoom in, it starts here, and this is a distance of r. And of course, this is the Earth's radius, which is also r. So first we want to find that once the ball reaches this during the first time, what is its v? Like, what is its velocity? So in order to find this, we can use conservation of energy. So E initial equals E final. First of all, initially it's not moving and it has a potential energy of negative gmm over r. So r is this whole thing, which is 2r. So it's 2 times the radius of Earth because the ball starts out at this far. And that is going to be equal to the final energy, which is the potential energy final plus the final kinetic energy. So 1/2 mv squared minus gmm over r. So we can solve this equation to get 1/2 mv squared. So I'm going to move this term to this side. 1/2 mv squared is equal to gmm over 2r. And 1/2 cancels out, m cancels out. So v equals the square root of gm over r. And if you're familiar with orbits, this is, in fact, if you look at the description of the problem, it says that v is the orbital speed at 0 altitude above the Earth. And it is, in fact, the same as the velocity when it hits the plate for the first time. So that means that, yeah. So the first time it hits, it's at v. But, of course, it will not be able to escape Earth because it comes back, right? It doesn't gain energy, even if there's no energy loss, but after the first bounce, it probably will come back because the Earth's gravity is pulling it. So in order to fully escape the Earth's gravitational field, we have to achieve something called escape velocity. And the escape velocity formula is given by VE equals the square root of 2 gm over r. And this is also calculated by energy. So that's equal to square root of 2 times square root of gm over r. And the problem defines V as square root of gm over r. So that's going to be equal to square root 2 times v. So we know that initially the velocity is at v, and it ends up being at square root 2 of v. So where does the ball get the extra energy? Well, it has to be from the elastic collisions with the plate. So we know that so velocity increase is going to be equal to the final one velocity minus the initial velocity. And that's going to be equal to square root 2 minus 1 times v. So we need to find what the velocity increase is. So let's focus more on this collision. Now there's this piston, right? It's moving up at speed v over 1000. And let's say the ball is moving at a speed of vb downwards. So first of all, since it's an elastic collision, we know that the relative speed of where it's colliding, or the plate, is going to be the same before and after the collision. So v relative before or initial is going to be equal to, well, think about it. If this is traveling toward it and this is traveling toward the plate, then relative to the plate, the ball will be traveling faster, right? Because they're trying to go towards each other. And that's going to be equal to VB plus V over 1000. So then V relative final is going to be equal to the also VB plus V over 1000, but in the opposite direction, because it's going to bounce up, right? So immediately after the collision. But then, remember that this plate is always moving upward at V over 1000. So relative to the plate, which is moving upward at V over 1000, this ball is moving up at VB plus V over 1000. But then we have to do it relative to the ground, because that's where all of our calculations for the velocity are set. Like, they're from the frame of the ground. So if we want to look at it from the ground, we have to consider both of these, because if you only look at the plate, it's this much. But then the plate is also moving away from the ground at this much, so you have to add them together. And then, so V relative to the ground is going to be equal to VB plus V over 500, because that's V over 1000 times 2. So we now have to, so this is going to be the required velocity increase. And remember that V ball is just, so V ball is going to be equal to, it's going to depend on the number of bounces, right? So every bounce, V ball increases by V over 500. So how can we find V ball in terms of let's say the number of collisions, right? Because every bounce it changes. So every bounce it increases this much, so the total is going to be the total increase. The total delta V is going to be equal to N times V over 500. And N is what we're trying to find here, because that's the number of collisions. And if we plug that into this equation here, we can get that N times V over 500 is going to be equal to our necessary change in velocity. And so we notice that V cancels out. Square root 2 is 1.414 approximately. So N over 500 is equal to 0.414. And we solve that n is equal to 500 times 0.207. Okay, but if you want it more accurately, square root of 2 is actually equal to 1.4142. So you get something like 207.2. Now, the question is it 207 or 208? Because the equation says that when it gets to 207.2, it can't escape. So think about it. That means that at 207, it doesn't escape, right? Because 207 is less than the necessary. But then you can have a fractional number of, oscillations because it's only in integers. So the next possible oscillation number is 208. And that is when the ball will escape. So our answer will be the answer choice B. Yeah. Now, thank you for watching, and if you have any questions, please leave it in the comment below, and make sure to like and subscribe. Thank you.